The web was objectively awful as a technology
Yeah.
and genuinely amazing. And nobody got into it because programming in Perl was somehow aesthetically delightful.
Oh man, that hits a little too close to home. I feel completely seen and attacked all at once.
Right. I mean, it's such a great observation. That is a quote from Kellen Elliott McCrae, and it's been making the rounds in engineering circles lately. And he follows it up with this really heavy, kind of nostalgic point about why we actually put up with how awful the web was back then.
Yeah, because it was terrible.
It was. But he says people our age were addicted to the feeling of agency. Like the web was messy, it was completely broken half the time. We were pasting scripts we barely understood, but it was ours. We were building it.
And the implication there, I'm guessing, is that today that feeling is gone.
Exactly. He contrasts that old Wild West feeling with this real feeling of loss that a lot of new engineers have today. You look at the modern stack, Kubernetes, React, these massive cloud infrastructures, and now AI writing the code for you, and it feels like the human is just sort of drifting, like we've
Yeah.
completely lost control of the machine.
Yeah, the loss of control narrative. I mean, the systems are just too complex to understand top to bottom now, so we just prompt and pray, hoping the black box spits out what we want.
But today, we're going to flip that narrative completely on its head. I brought a stack of sources for this deep dive that argue agency isn't dead at all. It's just undergoing a really radical redefinition. We are officially entering the era of agentic engineering.
Agentic engineering. Okay, that sounds very sophisticated.
It is. The core argument here is that your job isn't to write every single line of syntax anymore. It's to direct intelligent systems with extreme architectural precision. And to show you how this works, we're going to look at 3 very different optimization stories.
Right, lay them out for me. What are we looking at?
So first, we're breaking down the specific patterns top-tier engineers are using to turn AI into a rigorous tool rather than just a toy. Then we're going to look at the Ladybird browser team, how they use those exact patterns to do months of complex C++ to Rust migration in literally 2 weeks.
2 weeks for a browser engine port. I mean, that sounds frankly suspicious.
It does, doesn't it? But wait until you hear the actual methodology. Then we're going to get super technical on the hardware side with NVIDIA, looking at how to run massive reasoning models on tiny edge devices by squeezing memory until it basically screams. And finally, we have a curveball.
I saw this in the prep notes. We're pivoting to biology.
We are. We're going to take this exact same ruthless, data-driven engineering mindset and apply it to a biological optimization problem, specifically fertility and egg freezing. Because it turns out the standard industry advice has a massive bug in the data.
From Rust compilers to biological clocks? I like it. Let's dive in.
Let's start with the theory. This whole concept of agentic engineering really crystallized in a series of posts by Simon Willison. He's been documenting how the top 1% of developers are actually using these large language models in the trenches. And he identifies a pattern that is completely counterintuitive to how, most regular people use AI.
Right, because most people just open a chat window, say, write me a website, and then they just copy paste whatever comes out.
Exactly. And that is fundamentally wrong if you want reliable software. So the first pattern Willison identifies is something he calls, first, run the tests.
Which, to be fair, is pretty standard engineering advice. Test-driven development has been around for decades.
True. But the incentive structure has completely changed. In the old world, you wrote tests to verify your own work.
Right.
You asked, did I break this? In the agentic world, the test suite isn't just a verifier anymore. It serves a completely different function. It becomes a learning harness.
A learning harness. Unpack that a bit.
Think about dropping a really smart intern into a massive million-line code base. They have absolutely no idea where anything is. They don't know the variable names, the directory structure, the dependencies. They're flying blind.
Right. It takes human engineers months to fully onboard into a complex system.
Exactly.
Yep.
But if you have a rigorous test suite already built, and you tell an agent like Claude Code or a similar terminal tool to just run a command like run PyTest, the agent sees the output.
It sees all the failures.
It sees the failures, yes, but more importantly, it sees the stack traces. It sees the file paths. It sees exactly how the modules interact with each other.
Yeah.
By reading the test results, the AI builds a mental model of the system's constraints almost instantly. It's the absolute fastest way to context load the AI.
So the test suite basically becomes the documentation. The AI reads the error log to understand the architecture of the app.
Precisely. And it creates this incredible feedback loop. Willison calls it the red-green loop. The agent writes some code, runs the test, red light, it fails. The agent reads the error, self-corrects, and runs it again. Green light, it passes. It allows you to step back and let the agent iterate without you having to micromanage every single keystroke.
That makes a lot of sense. But it creates a new problem, doesn't it? If the AI is writing the code and then fixing the code to pass the test, the human is still totally out of the loop. Like, we've all seen vibe coding. You prompt an app into existence, it actually works, but you have zero idea how it works. That's not agency, that's magic. And magic is really dangerous in software engineering.
That is the exact trap. You build a cool demo, but you can't maintain it or scale it because you don't actually understand the source code. And that leads directly to Willison's second pattern, which I think is just brilliant. He calls it linear walkthroughs. This is all about reverse engineering your own creation.
How does that actually work in practice?
So Willison gives this great example. He vibe coded a slide presentation app in Swift UI. Now, he doesn't know Swift, he just prompted it. The app worked. But he felt that exact loss of agency you mentioned. He realized he needed to actually understand the code if he ever wanted to add complex features later. So he used a tool called Showboat.
Showboat.
Yeah, it's a tool that allows the AI to run terminal commands locally. He prompted the AI to write a walkthrough.md file, basically a linear tutorial teaching him how his own app works. But here is the kicker. He forced the AI to use grep and cat commands to pull the actual code snippets into the Markdown documentation.
Oh, I see what that does. It completely stops the AI from hallucinating. It can't just make up an explanation of how it thinks it works. It has to quote the actual compiled code it just wrote.
Exactly. It verified that the explanation matched reality. He essentially forced the machine to show its work step by step.
That is brilliant. It's like recovering your agency by forcing the AI to become your tutor. You're learning the language from the tool that just wrote it for you.
Right. And that takes us from these little toy apps to serious heavy-duty engineering. Because the skeptics will immediately say, sure, you can vibe code a little slide app, but you absolutely cannot build a browser engine that way.
Oh, yeah. Browser engines are the deep end of the pool. We're talking memory management, security sandboxing, incredibly complex rendering trees. You can't just hallucinate a browser and hope it compiles.
Enter the Ladybird browser project. We have this fascinating case study from Andreas Kling and his team. They had a massive task in front of them. They needed to port their JavaScript engine, which is called libjs, from C++ over to Rust.
For memory safety, I assume? Rust prevents a lot of those nasty memory leaks that plague C++ engine.
Correct. But rewriting a JavaScript engine is an absolute nightmare. It involves these deeply complex abstract syntax trees, or ASTs. Usually a port of that magnitude would take a dedicated team of senior engineers, months and months of just grinding work. They did it in 2 weeks.
2 weeks? That's incredibly fast.
2 weeks. And they generated about 25,000 lines of Rust code.
Okay, I have to play the skeptic here. 25,000 lines of code generated by an LLM in 2 weeks. That sounds like a buggy, unmaintainable mess. How much time did they spend just fixing the AI's mistakes?
That's the wild part. They reported 0 regressions.
0. That's statistically impossible for human engineers, let alone an AI hallucinating syntax.
It sounds impossible, but you have to look at how they did it. This wasn't vibe coding. This was pure architectural direction. Andreas didn't just open Claude and say, hey, rewrite libjs in Rust. He broke it down. He acted as the lead architect. He defined the memory model. He defined the structure. He used hundreds of small, highly specific prompts to steer the agents they were using, Claude Code and Codex, exactly where he wanted them to go.
So he was the general, and the AI was the foot soldier executing the tactics.
Exactly. But the only reason they hit 0 regressions, and this is the massive key takeaway, goes right back to our very first pattern, the tests.
They had a learning harness.
They had Test 262. That is the official ECMAScript conformance suite. It is absolutely massive and incredibly rigorous. Because they had that already in place, they could verify that the new Rust bytecode and the old C++ bytecode were identical.
Identical byte for byte.
Yes. They weren't just checking if the code sort of looked right or functioned mostly the same. They were solving a math problem where the answer key was already written in stone. If the bytecode didn't match perfectly, the agent had to retry.
Man, this really solidifies the agency argument for me. The agency wasn't in typing the syntax. I mean, who cares about typing braces and semicolons? The agency was in setting up the verification system.
100%.
Yeah.
The engineer becomes the verifier. You are defining exactly what good looks like, and you're letting the machine figure out how to get there.
Which really implies that to be an agentic engineer, you actually need more technical knowledge, not less. Like, you need to know how to write a conformance test suite for a compiler. You can't fake that with a good prompt.
Exactly. The floor has been raised significantly. And now I want to take this engineering mindset out of the code editor entirely and move it into the physical world. Let's talk about Edge AI.
This is the NVIDIA stuff.
Yes, we have a highly technical tutorial straight from NVIDIA on deploying something called Cosmos Reason 2B. Now, this is not just a chatbot. It's a VLM, a vision language model.
So it sees and speaks.
It reasons. That is the crucial difference. Old computer vision would just draw a bounding box around a car and output, car, 99% confidence. A VLM uses something called joint embedding.
Joint embedding. What does that mean in this context?
Imagine mapping raw video data and text language into the exact same vector space, the same mathematical coordinate system. So the AI can essentially read the video just like it reads a paragraph of text. This allows you to ask totally open-ended questions like, why did that car just stop suddenly? Or, is this environment safe for a toddler to walk through?
And you're running this on what? A massive H100 server rack in a data center?
No. That is the beauty of it. We're talking about the Jetson line, specifically the Orin Nano and the AGX Thor. These are small, edge devices. Think about a little aluminum box the size of a router sitting on a robot dog or a drone.
But running a reasoning model on a Nano sounds, wow, highly optimistic. VLMs are huge. The memory bandwidth alone on a Nano must be a massive bottleneck.
It is incredibly tight. It's like trying to fit an elephant into a mini fridge. And this is exactly where the agentic engineer earns their keep. You can't just pip install and pray. The tutorial breaks down the specific optimization stack required to actually make this work.
All right, walk us through the stack. How do you fit the elephant?
First, they use VLLM as the serving engine because it's highly optimized for throughput. Then they use a quantized model, specifically FP8.
FP8. So they're compressing the neural net weights from 16-bit down to 8-bit floating point. You lose a little precision, but you effectively have the memory usage.
Exactly. But on the Orin Super Nano, even that wasn't enough. They were still running out of RAM. So they had to use a very specific flag called enforce eager.
Eager execution. Usually you'd want to use pseudographs for speed, right?
Right. Pseudographs are like pre-planning your entire day before you even leave the house. It's super efficient, but it requires you to hold the whole schedule in your head, or in this case, in the VRAM. By enforcing eager execution, they basically told the GPU, don't pre-plan anything, just calculate the very next step and forget the rest.
So you sacrifice a little bit of execution speed to save the massive memory overhead of storing the graph.
Exactly. It's a calculated trade-off. They also had to use chunked prefill and aggressively limit the context window to just 256 tokens.
256 tokens. That is tiny. That's like, what, a short paragraph of text?
It is. It's just enough for a quick, what do you see right now, and a concise response. But it works. They connected this optimized stack to a live VLM web UI. You can hook up a standard webcam pointed at your desk, and the AI on this tiny little device gives you a running, reasoned commentary of what's happening in real time.
That's seriously impressive. It shows that we aren't just sitting around waiting for bigger, more expensive clouds. We're actively figuring out how to squeeze actual intelligence into smaller, cheaper boxes.
And speaking of tooling that squeezes performance, I have to give a really quick shout out to the Go ecosystem. In his post, Simon Willison highlighted a tool called Go Size Analyzer.
Oh, is that the one that runs directly in the browser?
Yeah. It analyzes all the dependencies in Go binaries to figure out why they're getting so huge. But the really cool part is that it's compiled to WebAssembly. You don't have to install anything on your machine. You just drag your binary into a web page, and it analyzes it locally right there. It's just another sign that our engineering tools are becoming much more accessible and instant.
You know, hearing all this automated tests, teaching agents, human architects directing 25,000-line ports, squeezing vision models onto edge devices, it really feels like the fundamental definition of an engineer is expanding.
It is. And organizations are starting to restructure because of it.
Yeah.
Did you happen to see the news from OpenAI about Arvind KC?
The new chief people officer they just hired.
Right. But look closely at his background. He is not a traditional HR admin. He's a hardcore engineer turned leader from Google and Roblox.
Which is pretty significant. Usually HR is, well, let's be honest, it's often completely disconnected from the actual engineering reality on the ground.
Exactly. But OpenAI is framing this role entirely differently. They're openly saying that as AI changes how work actually gets done, the people function needs to be about upskilling and navigating this transition responsibly.
That's a fascinating shift. It's them admitting that the structure of the workforce is going to fundamentally change. We aren't just hiring standard coders anymore. We're hiring these agentic engineers who need a totally different kind of support system and career path.
It connects right back to that agency quote from the intro. If we're moving from coding as manual labor to coding as architectural direction, we have to actually train people to be architects.
Okay, so we've optimized our code, we've optimized our hardware, we're optimizing our workforce. But you promised me at the start that we were going to optimize biology.
Yes, this is where we take the deep dive really deep. We found this fascinating analysis from Less Wrong by a writer named Gene Smith. It takes this exact same rigorous, data-driven engineering mindset we've been talking about and applies it to egg freezing and fertility windows,
Which is usually a topic full of, high emotion and very vague generalized advice.
which is exactly why it desperately needs an engineering approach. Think of your biology as a legacy system with a very hard deprecation date.
Clinical, but accurate.
Here's the premise. If you ask a standard fertility doctor right now, or look at the general industry guidelines, they will tell you the best time to freeze your eggs is in your mid to late 30s.
That seems pretty standard, the logic usually being don't worry about it until you actually need to worry about it.
Right. But if you look at the raw data, the actual logs of human biology, if you will,
Mm.
that advice is catastrophic. The data clearly shows the optimal age to freeze is actually between 19 and 26.
19 to 26. That is incredibly young. Most people that age are barely out of college. They certainly aren't thinking about children or affording fertility treatments.
Exactly. And that is exactly why the industry mostly ignores it. But let's look at the bug in the system. The source points out that SART, that's the Society for Assisted Reproductive Technology, reports all their success metrics in age buckets. And one of those primary buckets is simply under 35.
Oh, I see the problem right away. They're averaging a 22-year-old's fertility data with a 34-year-old's data.
Yes, it completely masks the signal. It's like averaging the top speed of a Ferrari and a Honda Civic and concluding, well, cars are generally pretty fast. The way they bucket the data hides the massive steady decline that happens specifically between age 24 and 34.
So if the industry metric is wrong, what is the actual metric we should be optimizing for?
Expected births per egg retrieval.
Okay, break that down for me. Why that metric?
Because standard IVF stats usually look at birth per cycle, meaning did this one specific implantation attempt work? But if you're thinking like an engineer trying to maximize yield, you want to know, if I put my body through one retrieval surgery today, how many babies can I expect from that single batch of eggs over my entire lifetime?
And that number drops fast as you age.
It drops off a cliff.
Yeah.
There's a 60% decline in expected births per retrieval between age 25 and age 37.
60%. Wow, that's the difference between doing one difficult surgery and having to do 3 or 4 of them. That's a massive difference in physical pain, financial cost, and time.
Exactly. And it gets even more complex when you add in polygenic screening. This is a newer technology where embryos are actively screened for genetic risks, things like Alzheimer's, diabetes, heart disease.
Which implies you need to be highly selective.
Right. This is a classic optimization problem. If you are selecting for specific health outcomes, you need a much larger pool of candidates, meaning more embryos, to find the optimal one. If you're freezing at 37, your yield is already incredibly low. If you then apply selection pressure on top of that, you might easily end up with 0 viable embryos. If you freeze at 25, you have the volume, the raw data to actually make those choices.
This sounds brutally efficient, but I mean, it's just math.
It is just math. And there's a trap people fall into here, which is very similar to the software world. It's technological optimism. People think, oh, in 10 years, we'll just be able to turn stem cells into eggs. It's called IVG technology, so I don't need to worry about freezing now.
Is that not true? I feel like I've read headlines about stem cell gametes recently.
The source is extremely skeptical about the timeline. It suggests we're at least a decade away from anything resembling commercial viability. And even then, stem cells accumulate mutations as your body ages. So waiting for tech that doesn't exist yet is a hugely risky bet. It's literally like deploying mission-critical code without a backup, just hoping the server upgrade happens before you crash.
So the fundamental takeaway here is remarkably similar to the Ladybird browser story. Do the hard work early, whether that's freezing young or writing the rigorous test suite so you actually have agency later.
Precisely. If you freeze at 25, you have optionality in your 40s. That's the ultimate form of agency. You aren't being forced into a corner by your biology. You have a backup that you explicitly engineered decades ago.
So bringing this all together.
We started with the fear that we are losing agency in the age of AI. But looking at all the evidence today, the Ladybird team directing agents to rewrite a browser engine, engineers shrinking reasoning models to run on a nano, and using raw data to debug biological timelines, I really don't think we're losing agency.
No. It sounds like agency is just shifting. It's shifting from execution to verification.
That is the key insight. In that Kellen Elliott McCree quote from the intro, agency came from the struggle, from doing the hard, messy work manually. In the agentic world, agency comes entirely from knowing what good looks like.
Right. You can't direct the AI to write a Rust port if you don't know how to write the test suite. You can't optimize an edge device if you don't understand eager execution flags.
Yeah.
And you can't optimize your fertility if you don't dig into the statistical bucketing.
We are officially moving from being the bricklayers to being the architects. But, and this is the final thought I want to leave everyone with, being an architect is actually much harder. It requires you to understand the entire system, not just the single brick sitting in front of you.
The real question is, are we ready to take responsibility for the whole building? Because what happens when the test suite itself becomes too complex for a human to verify? Who verifies the verifier?
That is the million-dollar question. Are we architects, or are we just going to end up as supervisors of black boxes? Something to mull over. As always, you can find the links to the Ladybird code, the NVIDIA Edge tutorials, and the raw fertility data in the show notes. Go explore them yourself and see what you think.
Thanks for listening.
See you in the next deep dive.